Hi folks, welcome to Ivy-GreGMAT Quant Intro Session Geometry. In the next 1 hour, we are going to understand the very basic concepts of geometry, the very basics, nothing, uh, the basic concepts. So nothing complex about it. So let me remind you before that, that this part, geometry, is no more a part of GMAT. The latest GMAT focused edition is not having geometry as a syllabus. So we can say that geometry is no more a part of GMAT. So hence the people who are aspiring for GMAT may omit this lecture altogether. Definitely forms a part of GRE. So with that understanding, let's start. Lines and angles seems to be very easy, or rather something which is which we have all learnt in our school days. But to get the very basic concepts clear, let us understand what line segments, rays and angles are. A line is a set of points extending indefinitely in two directions. Let's put it like this, that if a line is something, it extends in both the directions. So if you have said a line, it doesn't have an end point. But when I say line segment, it is a piece of line with two endpoints. So if there are two endpoints, and this is called as the line segment. On the contrary, a ray is a part of line with one endpoint. So a ray is going to be having one endpoint and it goes like this and it extends indefinitely. So if I do it like this is a ray. So an angle, what is an angle? An angle is made up of two rays. So say this is one endpoint, two rays that share the same endpoint called as the vertex. So this is the vertex. Fair? The angles can be, now we come to the angles that forms an angle here. So we coming to an angle can be an acute angle, an obtuse angle, a right angle, a straight angle, depending on the measure. So if I say the measure of the angle is between 0 to 90 degrees, it's an acute angle. If it is 90 to 180, it's an obtuse angle. If it is 90 degrees, it's a right angle. It's 180, it's a straight angle. So we will be basically dealing with these three types: acute angle, obtuse angle, and the right angle triangle. So rather, I will put it this way, that in GMAT, you will rarely come across, or rather in GRE, you will rarely come across obtuse angle. It's rather right angle and acute angle. So for our understanding sake, the more important part, or the most important part, is the right angle part. Now, complementary and supplementary angles, very commonly used terms. So complementary angle, two angles that have a sum of 90 degrees. So say if this is angle, this is 30 degrees and this is 60 degrees, we say they complement each other because the sum of 60 and 30 is 90, so they add up to 90 degrees. Supplementary angles, when two angles have the sum of 180 degrees. So say this is 50 degrees and this is 130 degrees. So they add up to 180 degrees. So that means that the two angles are supplementary to each other, or they are supplementary angles. Fair? The lecture is basically focused for those people who have left mathematics or are going to revise mathematics. So you shouldn't be surprised that they are so simple. I know them. Okay. So still, just a revision, quick recap. The drawings are in front of you, how they look like: an acute angle between 0 to 90 degrees, a right angle which is 90 degrees, generally designated like this, an obtuse angle which is 90 to 180 degrees. This is like this. more than 90 degrees. A reflex angle doesn't appear much here, but for our understanding's sake, this is 180 plus less than 360. Now the terms like adjacent angle, very popular, rather very common. Adjacent angles are A and B. You can see adjacent. They're living each beside each other. That way you can remember it. They add up to 180 degree. Now angles across a point. So if I have a point here, there can be multiple angles I can make across that point. If this is the point. So these are the various angles which can be there, like we have seen in this figure. So the angles across a point, the angles at a point, they add up to 360 degree. So every point, the total angle is 360. If I divide it into two, this is 180. Okay, okay, let's see. If two straight lines intersect, the vertically opposite angles are equal. Another important note, two straight lines, this one and this one, they have intersected here. So the vertically opposite, this one and this one. So A and B, C and D. A is equal to B. So A becomes equal to B and C becomes equal to D. A concept we will be using multiple times. Now, what are parallel lines? If I look at this drawing, it can become very easy. P and R is cut by a transversal LM, then we have something. Parallel lines are lines which will never meet. So it's not like this that they will meet somewhere here. Parallel lines are the lines which will never meet. They will keep going like this. A transversal is something that is cutting a parallel line. LM here is the transversal. Then the corresponding angles are equal. What are corresponding angles then? C and B. C and B are the corresponding angles. So it may be a figure like this also, where C is here and B is here. So C is equal to B. Similarly, the alternate angles. What are alternate angles? A and B. A and B. So if this angle is A and this is B, then A is equal to B. The interior angles are supplementary. That is B plus D. B plus D. So if I add up these two, they will always form 90 degrees. So if I add up these two, they will become two right angles, or rather 180 degrees. So if I add up these two, they are supplementary to each other. They will add up to 180 degrees. A clear drawing, I can say, will be something like this. It's not necessary that the transversal will be at 90 degrees. If it is like this also, then this angle C and this B are equal, as we saw here. A and B, this angle and this angle are equal. B and D, B plus D is equal to 180 degrees. Very basics of parallel lines. We'll be using it multiple times, or rather in questions they're never asked straight, or these are the basic rules of parallel lines. Let's see further. Triangles. Uh, we have all seen these figures. So what we need to know are the names. The vertex or the vertices is the corner. These are the vertices of the triangle. Every triangle has three vertices because it has got three angles, three sides. So three vertices. Base, the base of a triangle can be any one of the three sides. So it's not necessary that this is the base. For my calculation, this can be base. A very deceptive way of putting a triangle. It may be an isosceles triangle like this. A base is like this. So, uh, 1 second. Let me put it a bit better. I'm poor with drawings. So a triangle can look like this. I can treat this as the base. I can treat this as the base, whichever suits me. Because when I'm finding the area or something like that, when I'm calculating, anything can be the base. This is can be the base. This can be the base. This can be the base. It's not necessarily this is the base. So a smarter way of looking at it, I will treat any of them as the base and any of them as the height of the triangle. From there, I can make the height of the triangle. So the base of the triangle can be any one of the three sides, usually one drawn from the bottom. So we treat for our convenience this as the base. For calculating the area, etc., it is like half base into height. So this is the base, and and this is the height. So this is the area, right? So, so the next uh, term, vertex, base, altitude. The altitude of the triangle is the perpendicular from the base to the opposite of the vertex. If I draw a perpendicular, the altitude of the triangle is the perpendicular from the base to the opposite vertex. Opposite vertex means this. So this is the altitude. For our further understanding, not really used much, since there are three possible ways. There are three altitudes we can have, as we can see in this drawing. Three altitudes, they intersect at a single point, this point, which is called as the orthocenter. Right? Every triangle will have an altitude. From the base, you draw a line till the vertex. From this base till the vertex. From this base till the vertex. They meet at a point called as the orthocenter. Now, what is the median? Not the mean median mode. This median is the median of the triangle is the line from the vertex to the midpoint of the opposite side. So its altitude is something which starts from here and hits the vertex here. Median is which starts from here and hits the midpoint. This is the midpoint of the opposite side. So these two sides are equal. So similarly, a median from here makes these two sides equal. Median from here will make these two sides equal. As we can see in this diagram, the median has hit here from the opposite, from the vertex. So the three medians intersect at a point which is called as the centroid. This is called as the centroid. Each median divides the triangle into two similar triangles which have the same area. So once we draw a median, an altitude doesn't, but a median does. If this is a median, it divides the triangles into two parts, just to designate it as a different triangle. Two smaller triangles that have the same area. So obviously this is half the bigger triangle. So these are the two triangles. Triangle 1, or you can call it triangle 2. So two triangles having the same area, right? We have discussed these things. The centroid, the medians divide the triangles into 6 smaller triangles of equal area. So if I drop a median from every vertex, all the three vertices, then 6 smaller triangles are formed. 1, 2, 3, 4, 5, and 6. So this is 1, 6, so 3 is 3, this is 4, this is 5, and this is 6. So there are 6 smaller triangles of equal area are formed. Fine. Let's go further and see what is required. So with that understanding, we basically require in our exercise to find the area of the triangle, which is area of the triangle is half of the base into the height. So easily written is BH by 2. These two formulas, perimeter into R by 2 or ABC by 4, not really required. This will serve our purpose. Fine. But still for our understanding basis, this, if A and C are the sides, so if H is the length of the corresponding altitude, R is the radius of the circumcised circle, R is the smaller r is the radius of the incircle, and P is the perimeter, then also we can find the area by these two formulas. Okay, not very common in GRE, but this much is definitely required, and we'll make permutation and combination of this so that we can arrive at the area of the triangle. Also, if we do not know the base and the height, but we only know the three sides, then this person here on had come out with this formula called as this. Area of the triangle is actually root over of the s into s minus a, s minus b into s minus c, where what does s stand for? S is actually summation of the area of the sides a plus b plus c divided by 2, or the semi-perimeter of the triangle. Fine. The semi-perimeter multiplied by semi-perimeter minus the individual sides rooted over gives us the area. Fair? Okay. To extend this further, let's understand what is the perimeter. The sum of all the sides is the perimeter. Now, that's not important. What we need to know is for a given perimeter, equilateral triangle has the largest area. So if it is an equilateral triangle, means a triangle which where all the sides are the same for a given perimeter. So if the perimeter is say 20, which of the triangles will have the largest area? An equilateral triangle will have the largest area. It's not a scalene triangle or an isosceles triangle which will have the largest area. Say the perimeters are the same. It can be a long triangle, an equilateral, an isosceles triangle. It may be some haphazard kind of a triangle, but the one with the equilateral triangle will have the largest area for a given perimeter. Other way around, for a given area, equilateral triangle has the smallest perimeter. So if the area is given, say again 20 SQM square meter, for a given area, this equilateral triangle will have the smallest perimeter. So if there are three triangles of same area given, say 20 square meter or 20 square centimeter, whatever you say, the smallest area, the smallest perimeter will be of the equilateral triangle. Now we come to another level of understanding of triangles. The length of any side of the triangle must be greater than the positive difference of the two other sides, but smaller than the sum of the other two sides. To understand it simply, if there is a triangle, if A, B, and C are the lengths, say C is always more than A plus B. The length of, sorry, if A, B, and C are there, then this C, length of any side of the triangle, must be greater than the positive difference between two sides. C is more than A minus B. But also at the same time, smaller than the sum of the two sides. So C is less than A plus B. So that puts it right. I'm sorry for the goof up. So any third side, any side of the triangle is bigger than the difference of the two sides. Any side of the triangle is less than the summation of the other two sides. Very important property. We use it quite often, so we'll come across these kind of questions. Let's go to the next one. The interior angle. Three angles on the inside of the triangle at each vertex. So if I draw a triangle like this, these are the interior angles. The interior angles will add up to 180 degrees. If they add up to 180 degree, every angle must be less than 180 degree. But there is something which comes up again. The bisector of the three interior angles must meet at a point. So if I bisect them, if I bisect this angle, if I bisect this angle, they will meet at a point called as the incenter, which is the center of the incircle of the triangle. If I draw a circle like this, which is called as the incircle, they meet at a point called as the incenter. Once we are done with this interior angle, let's understand what are exterior angle, the angle between the side of a triangle and the extension of the adjacent side. So exterior angle, if I draw a triangle like this is an exterior angle. This exterior angle is equal to the sum of the opposite interior angles. Opposite interior angles. So if this is C and this is A and this is B, so C is equal to A plus B. Very important property. We will be using it time and again. So C, which is an exterior angle, is actually sum of interior angles. Similarly, if this is an exterior angle, this is equal to this plus this. So if this is an exterior angle, this is equal to this plus this. Let me draw it again. If this is a triangle, this is the exterior angle. This exterior angle. This is the interior angle 1. This is the interior angle 2. So E is actually interior angle 1 plus interior angle 2. Fair? Now comes another concept. Relationship of the sides to the interior angles of the triangle. In any triangle, the shortest side is always opposite to the smallest interior angle. So let's say the triangle is like this. One second. Looks something like this. The shortest side is always opposite to the smallest interior angle. By the very looks, I can find that, say, this is 90 degree. This is a larger side. This is the shortest angle. The smallest interior angle, and this is the right angle. This is an obtuse angle. This is an acute angle. Say this is 90. This is 30. And this is 60. So what it says is the shortest side is always opposite to the smallest interior angle. So this is the smallest interior angle. So this is the shortest side. The longest side is opposite to the largest interior angle. So here 90 is the largest. So this is the longest side. So in any triangle, it's not necessarily a right angle triangle. It may be a triangle somewhat looks like this. Say this is 35. Say this is 85, and this is whatever. So if this is the smallest angle, this side is the shortest. If this is the largest interior angle, this is the longest side. That much understanding is required. So that's the very basics of looking at a triangle. Let's go further. Rather, this is the most important part. right angle triangle. You can see this diagram of this triangle. We have done some marking here. ABC is the triangle. A triangle whose one angle is 90 degree is right angle triangle. This angle is 90 degree. So this is a right angle triangle. So with that understanding that one angle is 90 degree and it's called as a right angle triangle, B is a hypotenuse. This complete is the hypotenuse. And A and C are the legs. A and C, these are the legs of the triangle. These are called as the legs of the triangle. Called as the base and the height. This is the base and this is the height. Or let me clear it up. It looks a bit hodgepodge. This is the right angle. This is the hypotenuse. This is the base. And this is the height. This is hypo. That makes it clear. But we're going to play around with this because here something else has happened. AD is equal to N. AD is equal to N. And BD is equal to H. BD is equal to H. So a perpendicular has been dropped with a height H and M and N have been marked. With that understanding, we will go for some simple formulas. H square. So this perpendicular height H square is equal to M into N. M into N. We'll understand what is the Pythagoras theorem. AC square. So H square, uh, or rather the hypotenuse square is equal to the height square plus base square, or AC square is equal to AB square plus BC square. This gentleman Pythagoras came out with this theorem, and this comes pretty handy when we are solving right angle triangle problems. Extension of this H is equal to AC by B. So this H is equal to the base A into the height of the triangle C by B, the hypotenuse. AC by B is the length of the perpendicular that has been dropped. And we all know the area is base into height by 2. Important to note these two things, these three rather. This is relevant only in case of right angle triangle. Okay, so let's go further and understand the two variants we are going to play around with: 30 60 90 right angle triangle and 45 45 90 right angle triangle, or the isosceles right angle triangle. But what's so important about it is that in a 30 60 90 means a right angle triangle. Obviously right angle triangle means one angle is 90 degrees, the other two angles are 30 degrees and 60 degrees. We learned that the side opposite to the largest is going to be the largest angle is going to be the longest side, and the one against the smallest angle is going to be the shortest side. The ratio of the sides will be 1 is to root 3 is to 2. So if this is A, this will be A root 3, and this is going to be twice A. For our convenience, we are understanding. We don't have to derive a formula here. So in a 30, 60, 90 right angle triangle, again I am repeating, the side opposite to 30 degrees will be, if this is 1, then the side opposite to 60 degrees will be root 3. The side opposite to 90 degrees will be twice of A. Similarly, in a 45, 45, 90 right angle triangle, which is an isosceles right angle triangle, because obviously 45 degrees each, so the sides, the sides will be the same. The ratio of the sides will be 1 is to 1 is to root 2. So if this is A, this will be A, this will be A root 2. Think about it this way. This is a right angle triangle, isosceles right angle triangle. I can extend this like this. So it's actually square broken into 2. If I draw a square, and if I draw a line like this, okay, then the sides become A and A root 2. Simple Pythagoras theorem, which is this part, is actually square of these two rooted over. So that's why it's A root 2. In a cube, what happens, we'll learn later on. So let's keep it for that. So though it's given, the face diagonal is this in a cube, the body diagonal will be A root 3 and the surface area will be this, volume will be this. So we'll come to solid geometry. There we can discuss these things. Okay. Now, giving an additional treatment to this, the mid segment of a triangle, a line segment joining the midpoints of the two sides of a triangle. So this is a line that has joined the two midpoints of the triangle. So if I look at it this way, these are the two midpoints, and this is a line that is joined. The mid segment is always parallel to the third side of the triangle. This is so ED is always parallel to AC. Here also, this is one point. The other point is the mid segment is always half the length of the third side. So ED is half of AC. Now there is something called as basic proportionality theorem. The line segment to any one side of the triangle divides the other two sides proportionally. How? If D is parallel to BC. So let's draw a triangle here. A, B, and C. So this is D and this is E. If this is a triangle, this is our triangle. So we will get rid of this part. So this is an extension of whatever we are learning. So if DE is parallel to BC, then AD by BD, AD by BD is equal to AE by EC, this by this. Similarly, this segment by this is equal to this by this, and so on and so forth. So we can actually make multiple parallels here. So proportionality is there of the two sides. So the moment I join the midpoints, we can join these two midpoints. We can join these two midpoints and can find multiple proportionalities. So this basic theorem is required when we are solving questions. So let's see. Properties of similar triangles. Similar triangles are having the same shape, but they vary. Where they vary? They possess several key properties. They vary in size. If they vary in size, they have the same shape. Then how do we call them similar? Corresponding angles are congruent. Congruent means they are equal, and corresponding sides are proportional. So a triangle, say of this size, small, and a triangle of this size. They can be similar triangles. They can, though they look different, but they can be called as similar triangles. How come? Because their corresponding angles are congruent or equal. This angle and this angle may be equal, and the corresponding sides may, and this angle and this angle may be equal. This angle and this angle may be equal, and this side and this side may be equal, and this one and this one may be equal. This side and this side may be equal. So the corresponding angles are congruent or equal, and corresponding sides are proportional. What is required here are these three, rather this much. The length of the ratios. Similar figures, the ratio of the areas are like this. If the lengths are in the ratio of A is to B, the ratios of the areas are in. If the lengths are in the ratios of A and B, then the areas are in the ratios of A square by B square. So in the solids, this is A cube by B cube. That's it. Not much of a hassle here, but we may come across something like right angle similarity. ABC is a right angle, as we can see, right angle triangle with A as the right angle. So A is the right angle here. If AD is a perpendicular to BC, so this is a perpendicular dropped from BC, then triangle ABD, A, B, and D is similar to triangle CAD. Then we remember this one, DA square is equal to DB into DC. H square is equal to M into N, something like this. Say this is M, this is N. So recapitulating the old thing, quadrilaterals and polygons. What's a regular polygon? All the sides and the interior angles are same. We are going to deal with regular polygons only. We do not want to deal with absurd figures. Regular polygons are convex. That means they are always pointing outside. Let's draw a regular polygon. Let's draw something like this. A shape having equal sides, but 1, 2, 3, 4, 5, 6. So there are 6 sides. This is called as a hexagon. So this is a polygon. Regular sides, all sides and interior angles are same. So this angles and these sides are all same. So then only we can call it a regular polygon. They are convex. That means they are pointed outside. There can never be a absurd figure which has got something like this. We are not going to deal with such figures. So this is not there in our case. All interior angles are less than 180 degrees. So remember, all these angles, they are less than 180 degrees. All vertices points outward away from the interior. So obviously they are all pointing outside. Now, this is for our understanding. What comes handy are these two. The sum of the interior angles of a polygon is 180 multiplied by 2 minus n minus 2. Sum of the interior angles of a polygon are 180 into n minus 2. So where n stands for the number of sides. So it has got 6 sides. This is called as hexagon. So 180 into 6 minus 2. This is that 180 multiplied by 4. This is the sum of the interior angles. Other way around, just think about it. Whenever I am having a hexagon like this, if I take one of the vertices and start making triangles. So there are 1, 2, 3, and 4 triangles. So 4 triangles are there. we know, we know that the sum of interior angles of a triangle is 180 degree. So there are four triangles. So 4 into 180. Any polygon you take a square from one vertices. There are two triangles. So the sum of interior angles is 180 into 2. Or if I put it this way, 180 into n minus 2, which is 180 into 4 minus 2, which is 180 into 2. The formula comes pretty handy. So if I know this formula, then the other thing, each of the interior angles is, so what is the each of the interior angle? 180 into n minus 2, which is the summation divided by the number of sides. Okay? So we'll remember these two formulas only, or rather, this one formula is good enough to do our calculations. Basic idea of polygons can be drawn. Basic 4 5 types of polygons we are going to deal with are squares, rectangles, parallelograms, trapezoid, and rhombus. That's it. We will not deal with any other kind, hexagon, pentagon, octagon, etc. So to get a basic understanding of what is parallelogram or a quadrilateral, so this is why we say the parallelogram in quadrilaterals. This is one type of thing which we are going to use time and again. So a parallelogram is actually quadrilateral, but two sides are parallel to each other. So these two sides are parallel to each other. Properties of a parallelogram: the opposite sides of the parallelogram are equal in length. So if I so this side and this side are equal, this side and this side are equal. It can be like this also. So this side and this side are equal, and this side and this side are equal. The opposite angles of the parallelograms are equal in measure. So this is equal to this, and this is equal to this. So if this is A, B, C, and D, A is equal to C and B is equal to D. The diagonals of a parallelogram bisect each other. So diagonals will bisect. That means they will break up into two parts. Consecutive angles are supplementary. That means this plus this, or this plus this, are 180. Clear? Or this plus this, or this plus this is 180. Area of a triangle of a parallelogram is area is based into height, the base of the parallelogram, and the height of the parallelogram. So this is the base, and say this is the height of the parallelogram. So area is equal to base into height. Fair? So as we know, a parallelogram is a quadrilateral with opposite sides parallel and congruent. We can further extend it to something called as a square, a rhombus, or a rectangle. So what's a rectangle? Rectangle is a parallelogram with all sides fixed at 90 degrees. So that's same as square, but the sides differ. So that's the only thing different between rectangle and a square. But what's a rhombus? It's a parallelogram where all the sides are equal in length. This is important. Otherwise, it's all okay. It's just like a square where somebody has put in some pressure and it has become somewhat like this. The sides remain the same. All sides are equal. A, and A. Here also it's A, and A, and A. The sides are equal. A rectangle is a four-sided polygon with all interior angles at 90 degrees. So this is a rectangle. Say this is a sorry. That's all interior angles are 90 degrees. opposite sides are parallel and congruent. Opposite sides are parallel as well as equal. Two diagonals are congruent. That means if I draw D1 and D2, they are equal. Each diagonal bisects the other. So this diagonal will cut the other diagonal into two equal parts. So the point where the diagonals intersect or the cross divides each diagonal into two parts. So this is something that is dividing this and this, this and this. Each diagonal. Okay, fine. Squares. So we all know a square is a four-sided regular polygon with all the sides equal. Internal angle is 90 degrees. So just to recapitulate, the diagonals are also equal. So if I draw a square, something like this, let's draw it. These two diagonals. There are two diagonals. Uh, D1, say this is namely D2. So D1 is equal to D2. The length of each diagonal, D is equal to root of the sides. S root 2, where S is the side of the length. S, 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 S. This one. A square can also be defined as a rectangle with all sides equal, or a rhombus with all angles equal, or parallelogram with each diagonal that bisects the other angles. So this is one thing we find which we discussed earlier also. We can call it a rectangle with all sides equal, a rhombus with all angles equals, or a parallelogram with equal diagonals that bisect the angles. Now, if a circle is circumcised around a square, say this is a square, and I draw a circle around this, a bit of a change here. Let me draw it again. The area of the circle, this circle which is circumcised the square, is pi by 2 times the area of the square. Area of the square. If the circle is inscribed in a square, so if this is a square and the circle is inscribed in a square, it is pi by 4 times the area of the square. These two things you'll have to remember. Now another anecdote for us, a square has the larger area than any other quadrilateral with similar perimeter. So if any quadrilateral is there with a similar perimeter, this is the largest area you can have. Like we saw in triangle, equilateral triangle. Okay. So diagonals of the square, we know the lengths of the diagonals are equal. The area is half the product of the diagonal. So we have derived a formula here. So the area of a square can be d square by 2. Each diagonal of a square is perpendicular bisector of each other. That is, each cuts into two equal parts. So this is the property of a square, that they will be cutting each other and cutting each other at 90 degrees. A square is both a rhombus with equal sides, a rectangle with equal angles. Therefore, all the properties of both these shapes are there, namely diagonals of a square bisect each other, diagonals of a square bisect its angles, are perpendicular, both parallel and equal. All four angles of a square are equal. Diagonals are equal. So this is particularly a square-like. So nothing much to remember except this and whatever we learned in the previous slide. That much only. So now from square, let's come to a rhombus. Rhombus is basically a quadrilateral with all four sides equal in length. So it's a square where you put in a pressure and it has somehow turned the other way around and it has become somewhat squeezed. So this is a rhombus. So all the sides are equal. The angles are not at 90 degrees. It's a special type of parallelogram. Obviously, these sides are parallel to each other in rhombus. So this is parallel to this, and the sides are equal and are parallel to each other. The diagonals of a rhombus always bisect each other at 90 degrees. So if I draw a diagonal, this will be 90 degree. Now we can better see in these diagrams, the diagonals are at 90 degrees. The area of a rhombus, obviously base into altitude, base height. So it's basically a parallelogram where there is a base and there is a height. So if I take this as the base and this is the height, so or we can draw this rhombus again. This is the base and this is the height. So area is equal to base into height. That finishes with the rhombus. Trapezoid, a bit of a different looking figure. A quadrilateral where at least one pair of sides are parallel. So these two sides are parallel. These two are not parallel. Obviously, they are going to meet somewhere here. So a trapezium or a trapezoid is something like two sides are parallel. These two sides are not parallel. There is a base here. So if I use this, which is a healthier looking diagram, this is a base here. One of the sides, the leg of the parallel, the non-parallel sides. So these are the legs. And this is the altitude or the height. There is something called as median of a parallelogram of a trapezoid, which is like if I join the midpoints of the sides that are not parallel. The median of the trapezoid is the line joining the midpoints of the two legs. So this is the median. And this is obviously parallel to the base. Now, the length of the median is the average length of the bases using this formula. Average length of the bases. So median is equal to A plus B by 2. When I'm finding the area of a trapezium, it is height into the median, which is like we know the median is equal to A plus B by 2. So the area is equal to height into or height into A plus B by 2. Area is the average base length times altitude. So this much is enough. Trapezoid. For our understanding sake, something we can remember, we may remember, we may not remember. So better to remember. It's like few points here. These are the regular figures. and these are the number of sides. In a triangle has got three sides. The sum of the internal angles of the triangle is 180. Again, 180 into n minus 2 is the internal angle. This is the formula. Each interior angle, each interior angle is equal to 180 into n minus 2 by n, means the number of sides. Total summation of the interior angle is this. Each one is this. So if I can remember these two figures, my world will become much easier. If so, it's a triangle. The sum of the interior angle is 180. If it is a quadrilateral, it's 360. If it's a pentagon, it's 540. Hexagon, 720. Octagon, 1080. Fair. Now, once we are done with figures having vertices, having corners, let's talk about circles. Let me draw a circle first. May not be the an appropriate correct one, but okay, this will serve our purpose. The radius is the distance from the center. This is the center of the circle. This is the radius of the circle. If I add this part, this total is called as the dia of the circle, the diameter of the circle. If I take this point and go around like this and end up here, this is called as the circumference of the circle, the distance around the circle. Area is obviously the total area inside. The total of inside is the area of the circle. A chord is a line segment linking any two points in the circle. So diameter is also a chord which passes through the center, but a chord may be anything. These are all chords. A chord may be a very small one. A chord may be as long as, or rather the diameter is the longest chord because it passes through the center. So if this is the circle, the dia is the, and if it passes through center, the chord passes through the center, then it is the diameter. If the chord passes from here, it is definitely smaller than the diameter, though it is called as chord. This is also a chord. This is also a chord. They are all called as chords. Now, what is a tangent? A line passing a circle and touching in just one point. So, a tangent is something which passes like this, just touches in one point. This is a tangent. Now, there's one property. The tangent line is always at 90 degrees, or rather perpendicular to the radius of the circle. So if I draw a tangent here, there's a circle here, and there's a tangent here. So where it touches, it is at 90 degree with the radius. This is the tangent and this is the radius. So this is 90 degrees. A line that intersects secant is a line that intersects a circle at 2 points. This is secant. Intersects the circle at 2 points. So it's a chord which is extended. Fair? Now many of us know the formula pi r square, etc. But what is a pi? The pi is a constant. Pi of in a circle, if you divide the circumference, the this length by its diameter, you will get a same number. No matter how big the circle is. If circle this small or a circle this big, this ratio of dia by this ratio of circumference by the radius is same. This number is called as pi, and approximately 22 by 7, which is equal to 3.14. Important fact of a circle is that the shape with largest area for a given length of perimeter. So if there is a perimeter of any object, of any shape, the largest will be of a circle. Another thing, to form a unique circle, you have to have 3 points. If there are 2 points, you cannot draw a circle. You have to have 3 points. So in order to make a circle, it may be a circle of this size or it may be a circle which is of this size. So you need 3 points. Okay? Let's do a bit of an experimentation with the circle. Something comes inside, goes outside. So circumference, perimeter of a circle has got a story behind it. Let's see. Given the radius r, the circumference can be calculated using the formula 2 pi r. Very popular formula, or pi d. This is the circumference of a circle, 2 pi r or pi d. Just remember these two formulas. Area of a circle, pi r square. You may not remember them, keep them in mind. Or this much only will do. You may not remember this. This much one must know. But the situation changes in a semicircle by dividing it by half. So pi r square becomes pi r square by 2 as far as area is concerned. Perimeter doesn't become 2 pi r by 2, becomes pi r for the, this much is pi r. What about these two? This is 1 r, this is 1 r. So perimeter adds up 2 more radiuses. So 2 r. So we simplify it further. R into pi plus 2. Now there is something interesting that happens in a when there is a semicircle. Let's see. The the angle inscribed in a semicircle is 90 degrees. So this is 90 degrees. So no matter what is the size of the circle, 1 second. Say let's draw a circle that's this big. If this is the diameter, if I make any angle anywhere in the circle, anywhere, this is bound to be 90 degrees. Say this angle was made here. This is 90 degrees. Let me change the pen. See if I draw an angle here. This angle. So this becomes 90 degree. The angle inscribed in a semicircle is always 90. This property we are going to use time and again. Any diameter of a circle subtends the right angle at the point on the circle. No matter where the point is, no matter, it may be here, here, or here, anywhere. But this is going to be 90 degrees. Fair? Okay. Chord. We know a line that links 2 points on a circle. So, but with that comes a new chapter, the angles in a circle. An inscribed angle is an angle ABC formed by points ABC on the circle. This is called as an inscribed angle. And there is something called a central angle. an angle with endpoints A and C located on the circumference and vertex O located in the circle center. Now, with this understanding, something else happens. Whenever there is a circle, the central angle theorem comes in the picture, which states that the measure of the inscribed angle is always half the measure of the central angle. Let's understand it further. If I draw an angle here, say this is 60 degrees, then this is 30 degrees. Say this is 80 degrees. Then if I draw an inscribed angle here, this will be 40 degrees. Got it, folks? So that's the central angle theorem. Let's see arcs and sectors. Minor arc, major arc. So uh, fairly simple. This is this length. This is the minor arc, and this is the major arc. The length of the arc L is equal to 2 pi r, which is the circumference into C by 360, which is the central angle. Similarly, the area, but the arc makes something called as a sector. The area of a sector is pi r square, which is the total area, times C by 360, which is C is the angle alpha. So if it's say area of this sector, which is, if I draw the area of this, pi r square into alpha by 360. If I say the length of this arc, L, is equal to 2 pi r multiplied by alpha by 360. The last but not the least point theorem comes pretty handy sometimes when we are dealing with this kind of a situation where there is a point outside the circle. Then PA multiplied by PD is equal to PC by PB. So if there is a circle like this and there is a point here, from this point originates a line that hits the other side, both the sides of the circle. Okay. So this is P, this is A, this is D, this is C, and this is B. So PA into PB, PD is equal to PC into PP. Point theorem. This is the first part. If this point is inside the circle, P is inside the circle. So PA multiplied by PD becomes PC into PB. Interestingly, if there is a tangent or secant, which is like this, so PA into PD, but PA and PD are the same, and PC and PB. So PA into PD, as is here, is equal to PC into PB, which is constant. So since this is not there, so PA square is equal to PC into PB, which is again a constant. Now, taking an extension from there, if you've got two tangents, then it becomes PA square is equal to PC square. That makes it PA is equal to PC. From any point. Now remember, from any point, if I draw a circle like this, from any point outside, if there are two tangents drawn, they are of equal length. No matter how far the point is, this is equal to this, or how near the point is. This length and this length are same. So that brings us to the end of two-dimensional geometry, which is more relevant as far as GRE is concerned. Let's just glance over the solid geometry part so that we can recapitulate or remember whatever we learned long back in the school. A cube, a three-dimensional figure, which can be called as an extension of a square. A cube is a 3D generalization of a square and is characterized by the length of the side which are all equal. So if A is A is A, it's A. So all the sides are equal. So the volume of the cube is A cube. Surface area is 6A square. The diagonal length is root 3A. So this is like, if I draw a diagonal, or rather a cube is like this from this point, not this point, but if I want to touch, uh, let me change the pen. If I want to touch this point, this is the diagonal I'm talking about, which is root 3A. In case of a cuboid, the formula changes a bit. Let's see how. A cuboid has got all the three sides which are different. So A, B, and C. So if this is A, this is B, this is C. So, or you can, for our convenience, this is A, this is B, and say this is C. Length, breadth, and the height. So the volume becomes A, B, and C. The surface area is twice of AB, BC, and CA. The length of the diagonal is root over A square plus B square plus C square. Clear? So these are the formulas you need to remember. That's it. I think that will serve our purpose. Let's see the other 3D figures. A cylinder. Cylinder is nothing but when a sheet of paper. Say, one second. Say a sheet of paper is wrapped up, and this end is touched to here, and this end touches here. Then you get something like this. If I get something like this, then the volume is this circle which is formed into the height. So pi r square multiplied by h, because this is the area of the circle that is formed and the height. So pi r square into h. Outer surface area is actually the this circumference, which is 2 pi r as the length of as the circumference of a circle into the height. So 2 pi r h. This is the outer surface area, only the outer surface area. But if I add up these two areas, one at the bottom and this one, or rather, let me put it this way, this one and this one, then something else happens. 2 pi r multiplied by r plus h. A cone looks something different, but if I put a treatment to it, it will look easy. A 3D object like this must have seen. This one is the slant height, this is the original height, and this is the r. So if I make a cone, it has got a larger base with the tip on the top. So what is the length of this one? This length is actually root over r square plus h square, because we are getting a kind of a triangle here, because it forms a circle in the bottom. There is a r here, there is a height here, so this slant height L is rooted over r square plus h square. Simple. Now question arises, what is the volume of a cone? So 1/3 of pi r square into h. So actually, if you look at this cylinder, it can accommodate 3 cones, because pi r square h is the volume of a cylinder, but 1/3 of it makes the volume of a cone. The outer surface area is pi r L, pi r into L, where L is, we know, this. So that has been replaced here. So pi r into rooted over r plus h square. The outer surface area, including the base, is pi r r plus L. Fair? Okay. A sphere. Sphere is nothing but a ball, we all know. Two formulas which will play a role. 4 by 3 pi r cube is the volume of a sphere. Surface area is 4 pi r square. Hemisphere just divided by 2. 2 by 3 pi r cube, 2 pi r square. This is without the base, because obviously there is a base here. If I do not take into account this surface area, then this is the thing. But if I include this surface area also, then it is 2 pi r square plus a pi r square here, area. So it becomes 3 pi r square. Okay, this part is not that important, but still, sphere inscribed in a cube of side A. The radius of the sphere is a by 2. Side of the cube is 2r by root 3. Cylinder inscribed in a cube of side A. You can derive these, the radius, height A, etc., etc. So cone inscribed in a circle, the cylinder of radius r in a sphere. So these are just additional things which are given. So you may. This is basically a recapitulation of the entire thing. You can note it down. I believe you must have already noted it down. Anyway, just for understanding's sake, I am making it a point that I read it for you. Two angles whose sum is 90 degree are complementary. 90 degrees complementary, 180 degrees they are supplementary. They both mean the same thing, that one is the complement of the other. The each is complement of the other, is a supplement of the other. The sum of the interior angles, we know, of a triangle is 180 degrees. In a triangle, an exterior angle is the sum of the two interior angles. So we learnt it. This angle x is equal to y and z. So x is equal to y plus z. In a triangle, the sum of any two sides is greater than the third side, and the difference of any two sides is less than the third side. We saw it like in a triangle with sides A, B, and C. C is always less than A minus B or B minus A, and C sum of any two sides is greater than the third side. sum of any two sides is greater than the third side, and the difference of any two sides is less than the third side. In a triangle, the sides opposite to the greatest angle are greatest, and vice versa. ABC denote the triangles. If C square is this, okay, fine, we have obtained this. Sum of the four interior angles of a quadrilateral is 360. Obviously, a polygon, the sum of the exterior angles is this 360. Another way of representation, this is 180 into n minus 2. You can make it 90 into twice n minus 4. The same thing. Angle in a semicircle is a right angle. So if there is a circle in a semicircle, any angle is a right angle. Any angle acceptance is a right angle. So with that, I think we have covered the entire geometry portion in theory. Whatever happens, understood the basic concepts. So to build upon that, when the sessions happen, you go to the sessions, you'll find questions which are relevant or rather related to the concepts only. We have pulled the questions have been pulled out, keeping these concepts only in mind. So that is it. Thank you very much.